Welcome to our video tutorials for our PC tool openSYDE. In this video, we would like to demonstrate the feature code generation. If you are not yet familiar with the basics of openSYDE, we recommend the video Basic Introduction to openSYDE from this series. openSYDE collects a lot of data about the configuration of your system during the system definition stage. For programming single components of the system, this data can already be used to generate code in various programming languages. In this video, we show you the generation of C code. For demonstration purposes, we use a controller ESX4CSGW from STW. This controller has an LED that can be controlled by software and displays different colors and blink codes. We use this simple programming of the LED to show the basic principles of code generation. In another video, we will look at more complex programming such as CAN communication. The data pools play a central role in code generation. In addition to code generation, these can also be used to create displays and controls in the dashboards of openSYDE and thus influence the behavior of the LED at runtime starting from openSYDE. We will show you the interaction of openSYDE, Integrated Development Environment IDE, and the controller. We will create a data pool with a variable list with openSYDE, generate code and thereby make the data pool with the variables usable for programming. Program an application and flash it to the controller. And finally, change the variables at runtime with openSYDE and visualize the values. The basis for this video is the sample project included in the target support package so that you can reproduce the processes shown here yourself. First, we need to create an experimental setup with all the necessary hardware and software components. For programming in the programming language C, we need software which you can obtain via the cloud at STW. You will receive access to the cloud from STW Sales when you have purchased the components. You will need the development environment LogicCAD 3, the C compiler from Hitech, the target support package for ESX4CSGW from STW, the openSYDE package. In this video, we assume that the components are already installed on the PC. Now we can document the setup in openSYDE. We start openSYDE and open a new project. We are using a 4CSGW. We connect the Ethernet interface of the controller because we want to benefit from the high performance of this interface later during programming. openSYDE thus communicates with the controller via Ethernet. Alternatively, we could also have used the CAN interface. We save this new project in a directory of our choice on the PC. Here you can see this experimental setup in reality. A USB to Ethernet adapter is installed on the laptop running openSYDE. The Ethernet interfaces of the adapter and the controller are connected with the green patch cable. The controller is connected to a power supply via a standard cable set such as you get with the starter kits from STW. Next, we prepare the software components in the openSYDE project and recompile the template project in the development environment for trial purposes. Since we have already downloaded the target support package for the ESX4CSGW from the STW cloud, to create the data blocks we can import them from there. We navigate to the openSYDE TSP in the package. Since the ESX4CSGW is a multi-core controller, a separate data block with its own application is created for each core. So, by importing, we create 3 applications whose code we can edit later in the development environment. The application on the boot core has mainly the task to start the controller with the applications on the other cores in an orderly way. This is usually not changed. Therefore, no code generation is enabled for it. When using functional safety, the application on the safety core is used to record the safety code. Here, all the minimum necessary functions are already programmed by the template. You could generate code for this application, but we will not edit the application in this tutorial. The application on the application core contains the non-secure code. Here we also find the programming of the LED. We can also generate code for this application. Here, through the template, all the minimum necessary functions for operation are programmed as well. By adding the controller to the project, an IP address is provided for the Ethernet interface. We adapt this to a valid IP address for our network used here. If we look at the data block for the application core in detail, we can see the following important settings. The project can be loaded later in the development environment. The ID is defined with name and path relative to the openSYDE project. The name and path of the hex file, which is created later by compilation in the IDE, is defined as output file. In the field IDE call, a command for starting the development environment is stored. Here it is LogicCAD with the C perspective, because we will program in C. The paths used here correspond to the default values suggested during the installation of LogicCAD. As code generator, we use the openSYDE Coder C, which is already available in openSYDE. The code structure version depends on the software components used. It can be taken from the user manual of the controller. Here it is version 4. The process ID is required for multi-core controllers such as the 4CS-GW. In the directory Gen directory, the code is stored, which is generated by openSYDE during file generation. Let's take a quick look at what the import of the 3 data blocks did in this file system. We see that underneath the openSYDE project, a directory named ESX4CS-GW has been created. It contains further directories for the application of the 3 cores. For example, in the directory for the application core, among other things, a directory with the designation SRC has been created. It contains the program main C, which we will now edit further in the IDE. Below this directory, there is also the directory openSYDE, which contains the C files for the integration of the openSYDE server into the application, and another subdirectory for code generated by openSYDE. Back to openSYDE. So we start the IDE. We can do this from openSYDE. LogicCAD starts immediately with the so-called C perspective, i.e. the configuration for programming a C project due to the settings made. We open the folder just found in the file system with the C project for the controller. To make sure that the project and the installed development environment, including compiler, are working, we create the hex files for the 3 applications from New. To do this, we select Build Configurations with the right mouse button and create the Release configurations. The progress of the process is displayed in the console window. We should not get any errors or warnings as seen here. We can see by the date in the File Explorer, as seen here in the example of the application core, that the hex files have been regenerated. We now want to flash these newly created hex files to the controller. For this we use openSYDE. In our view, we go into the update mode. We can recognize this mode of the controller by the behavior of the LEDs. openSYDE detects that for each core there is a newer hex file than the one on the controller. So we click Update and flash the hex files. Leaving the update mode triggers a reset in the controller and starts the application. We can see this again in the behavior of the LEDs. We briefly summarize where we are now. We have imported the supplied template into openSYDE from the TSP. We have opened the resulting C programming project in the development environment LogicCAD in the C perspective. We have recompiled the template unchanged for testing purposes. We have flashed the resulting hex files to the controller. Thus, we have successfully put our application for programming into operation with respect to the development environment and openSYDE. We now start programming the behavior of the LED of the controller. The communication between openSYDE and the controller runs via datapools and the diagnostic protocol. Datapools are set up in the system definition for the components of the system. So first we need a data pool of the type diag for the desired functions. Thus we add a data pool and name it LED control. We enter a comment. Since we know that the LED control is programmed in the application on the application core, we also assign the data pool to this data block. This assignment must be present for successful later code generation. For the three functions, we now need three data pool variables. Since we have newly created the data pool, a list with a variable has already been created too. We will now adapt the variable for the first function. We want to be able to switch the LED on and off. We give the variable a meaningful name and add a description. It will accept only two values on and off respectively. And we will be able to read and change the variable. To program the intensity and color of the LED, we have to look in the user manual of the controller to see what functions are available in the BIOS for this purpose. We find several functions for this and recognize in the XLED set blend function values from 1 to 10,000 for intensity and values of 1 to 10,000 for the color spectrum from green to red. So we need another type uint32 variable for the intensity, and we add one. We set the minimum and maximum value according to the specifications in the user manual. In the same way, we set another variable for the color spectrum, also with the values from the user manual. We will now look at how openSYDE supports us in generating the required code for LED programming. We first save our project and click on Generate Files. openSYDE shows us for which data blocks code is now generated. The files for the code are always generated completely new and the directory is deleted before. A report is displayed at the end. We see in the file directory for the generated code that more C and H files have been added. To see the contents of these files, we switch to the development environment and navigate to the appropriate location in the project. We press the key F5 to refresh the display and see the files for the LED control data pool. The content of the generated files includes the code for the structure definitions. openSYDE relieves us of this extensive typing by generating the code. We just need to include this code into our application. So we open main C in the development environment. We recognize the current programming of the user LED in the implementation area. As long as the controller does not go into reset, a function handle LED is called, which changes the color of the LED step by step by means of the BIOS function xLEDSetBlend. We now want to replace this by controlling the LED behavior using openSYDE. We first include the data pool. Then we initialize the data pool variables in a suitable place. We can use the autocomplete function to do this. And we replace the hard-coded behavior of the LED with a logic that controls the behavior of the LED depending on the values of the variables LED intensity and LED color. We create the hex file for this application. It is enough to select only the configuration for the application core, because we have changed only this application. We switch to openSYDE and update the system. openSYDE recognizes that only the hex file for the application core needs to be flashed. The other cores are not flashed. We exit the update mode and the controller performs a reset. The new application is running and we can already recognize the changed behavior by the constantly green lit LED. Now we have to build a user interface into openSYDE where the user can switch the color change on and off and set the static values for color and intensity. To do this, we use the dashboards in our view under System Commissioning. We click on Edit. To switch the color change on and off, we use the toggle widget from the toolbox. By double-clicking or using the right mouse button, we can edit the properties of the widget. We want to change the variable LED run via the widget, so we select this as the data element. Whenever a change is made, the variable should be updated. Finally, we add a description. For setting the intensity, we use a slider widget. As data element, we choose the variable LED intensity, which should also be updated again with every change. We want to read out the set value. For this we use the value widget. We assign LED intensity as a data element to this as well. In the same way, we create the possibility of setting the color value. Our dashboard is ready. We click Confirm. Now we check the functions. We go online with the dashboard. By linking the widgets to the data pool variables and transferring the values between the PC tool and the controller, the LED behavior is now controlled via the functions of the application. If you switch on the color change with the toggle widget, the color of the LED is changed in 4 steps. If you switch off the color change with the toggle widget, the settings of intensity and color can take effect and be adjusted via the sliders. We summarize once again. openSYDE supports the programmer with the generation of code parts. Data pools are used to hold the data. Lists of variables can be created quickly and conveniently in openSYDE. Code generation converts the data pools into C and H files. Structured definitions no longer have to be written by the programmer. Data pools are integrated by the programmer into the own application and can be used directly for the functions of the application. In openSYDE, the data pools can be used in dashboards to change variable values or to visualize them. In the series of openSYDE videos, other videos appear on this channel that deal with the details of individual features. I wish you every success using openSYDE.